The cosmos, in all its vastness and splendor, presents us with endless mysteries. Among these, the enigma of antimatter stands out as a particularly perplexing puzzle. Antimatter, a concept seemingly ripped from the pages of science fiction, is very real. It exists as the mirror image of ordinary matter, possessing the same mass but with opposite charge. Imagine a universe where particles have their counterparts, identical in every way except for their charge. Protons, the positively charged building blocks of atoms, are mirrored by antiprotons, their negatively charged twins. Electrons, the negatively charged particles orbiting atomic nuclei, have their positive counterparts in positrons. The existence of antimatter was not merely a theoretical fancy. It was predicted by physicist Paul Dirac in 1928, and soon after, in 1932, the positron was discovered by Carl D. Anderson. This discovery sent ripples through the scientific community, confirming a fundamental symmetry in the universe. However, this symmetry presented a profound paradox. If matter and antimatter were created in equal amounts during the Big Bang, as the theory goes, why does our universe appear to be dominated by matter? Where did all the antimatter go? This is a question that has puzzled physicists for decades. The story of antimatter begins in 1928 with Paul Dirac's groundbreaking work on combining quantum mechanics and Einstein's special relativity. Dirac's equations, elegant in their mathematical beauty, predicted the existence of a new particle, one with the same mass as the electron but with a positive charge. This particle, dubbed the positron, became the first antiparticle to be theorized. The theoretical prediction of the positron was met with skepticism. However, doubt gave way to astonishment when, in 1932, Carl D. Anderson observed the tracks of positrons in his studies of cosmic rays. Anderson's discovery, a pivotal moment in the history of particle physics, provided the first experimental confirmation of antimatter. Further research revealed that every known particle has a corresponding antiparticle. Protons have antiprotons, neutrons have antineutrons, and so on. When a particle and its antiparticle meet, they annihilate each other in a burst of energy, a process that has captured the imagination of science fiction writers and scientists alike. At the forefront of this exploration into the world of antimatter stands CERN, the European Organization for Nuclear Research, home to the world's largest and most powerful particle accelerator, the Large Hadron Collider. Within CERN's sprawling complex of underground tunnels and sophisticated detectors, scientists are pushing the boundaries of our understanding of the subatomic realm. CERN's unique facilities allow for the creation and study of antimatter in quantities and with a precision never before achieved. The antiproton decelerator, a specialized machine at CERN, slows down antiprotons produced in high-energy collisions, making them suitable for further study. Among the numerous experiments at CERN, the ALPHA experiment, short for Antihydrogen Laser Physics Apparatus, stands out as a beacon in the quest to understand antimatter. The ALPHA collaboration involves scientists from around the world, all united by a common goal: to unlock the secrets of antimatter and its relationship to the universe we inhabit. The ALPHA experiment is a marvel of modern physics, a testament to human ingenuity and the pursuit of scientific knowledge. Its heart lies in a complex apparatus designed to create, trap, and study antihydrogen, the simplest antimatter atom, consisting of an antiproton orbited by a positron. Creating antihydrogen is no easy feat. It begins with the production of antiprotons, which are then slowed down to manageable energies in the antiproton decelerator. These antiprotons are then carefully guided and merged with positrons, their antimatter counterparts. The result of this delicate dance is the formation of antihydrogen atoms. However, antihydrogen is notoriously difficult to handle. Its neutral charge makes it impervious to the electromagnetic fields typically used to trap charged particles. To overcome this challenge, the ALPHA experiment employs a sophisticated magnetic trap, a technological marvel that confines antihydrogen atoms using their subtle magnetic properties. Section 5. Alpha G Unveiling the Gravitational Nature of Antimatter. One of the most fundamental questions surrounding antimatter is its gravitational behavior. Does antimatter fall down under the influence of gravity, just like ordinary matter, or does it perhaps fall up, as some theories have suggested? This is a question that the Alpha G experiment, a specialized version of the ALPHA experiment, was designed to answer. The Alpha-G experiment, housed within a tall cylindrical vacuum chamber, is a testament to the precision and ingenuity required to probe the fundamental nature of antimatter. Antihydrogen atoms, once trapped within the experiment's magnetic confines, are released in a controlled manner. Their subsequent motion, tracked with exquisite sensitivity, reveals the influence of gravity on these exotic atoms. The experiment's findings, eagerly awaited by the scientific community, have the potential to revolutionize our understanding of gravity and its relationship to antimatter. Does antimatter truly obey the same gravitational laws as ordinary matter, or does it hold the key to new and undiscovered physics? Section 6. Deciphering the results, implications for our universe. After years of meticulous preparation and data collection, the Alpha-G experiment yielded groundbreaking results. The experiment demonstrated that antihydrogen, the simplest antimatter atom, falls under the influence of gravity, just like its matter counterpart, hydrogen. This finding, a resounding confirmation of Einstein's theory of general relativity, has profound implications for our understanding of the universe. The fact that antimatter falls down, rather than up, rules out certain exotic theories that proposed anti-gravity as an explanation for the universe's matter-antimatter asymmetry. These theories suggested that antimatter might have been repelled by matter in the early universe, leading to their separation and the dominance of matter we observe today. While the Alpha-G experiment's findings have provided crucial insights, the mystery of the missing antimatter remains unsolved. If matter and antimatter were indeed created in equal amounts during the Big Bang, where did all the antimatter go? What subtle differences between matter and antimatter led to the universe we see today, a universe teeming with stars, galaxies, and life itself? Section 7. Lingering questions and the quest for answers. The Alpha-G experiment, while groundbreaking, has not answered all our questions about antimatter. In fact, it has raised new ones, pushing us to delve deeper into the realm of the very small to understand the workings of the very large. One of the most pressing questions is the nature of the interaction between antimatter and gravity. While the Alpha-G experiment has shown that antimatter falls down, the experiment's precision leaves room for subtle differences in the gravitational acceleration of matter and antimatter. Future experiments, with even greater sensitivity, will be needed to explore this possibility. Furthermore, the mystery of the missing antimatter persists. The Alpha-G experiment's findings, while ruling out certain exotic theories, have not provided a definitive answer to this fundamental question. The search for the missing antimatter continues, driving physicists to explore new theoretical frameworks and develop ever more sophisticated experimental techniques. Section 8. The future of antimatter research, unlocking the cosmos' secrets. The study of antimatter is a journey into the heart of the universe's mysteries, a journey that is far from over. The Alpha experiment, along with other experiments at CERN and around the world, continues to push the boundaries of our understanding, unraveling the secrets of this elusive and enigmatic substance. Future research directions include improving the precision of antimatter gravity measurements, searching for subtle differences between the properties of matter and antimatter, and exploring the possibility of creating more complex antimatter structures, such as anti-atoms and even anti-molecules. The insights gained from antimatter research have the potential to revolutionize our understanding of the universe. By studying the properties of antimatter, we are essentially peering back in time, glimpsing the conditions that existed in the earliest moments after the Big Bang. Section 9. Conclusion: a universe of mysteries yet to be solved. The universe in all its vastness and splendor is a place of endless wonder and mystery. The study of antimatter, a substance both familiar and profoundly strange, lies at the forefront of our quest to comprehend the cosmos. From the first theoretical predictions of Paul Dirac to the groundbreaking experiments at CERN, our understanding of antimatter has come a long way. Yet the journey is far from over. The mystery of the missing antimatter, the question of why our universe is dominated by matter, continues to tantalize and inspire physicists worldwide. As we delve deeper into the subatomic realm, we can expect even more surprising discoveries that will challenge our current understanding and illuminate the path toward a more complete picture of the universe and our place within it. The future of antimatter research is bright, filled with the promise of unlocking some of the universe's most closely guarded secrets.